and this was important. Then we found the polynomial fx of degree at most k minus 1 such that satisfying various conditions. F of x1 is y1, f of x2 is y2, so on. So this was the third thing we did, and for this, in the course of proving this, we discussed the van der Monde determinant. Okay. Then the fourth thing we did was we were trying to see how both of these results, that is, how both Lagrange interpolation as well as the Chinese remainder theorem are special cases of one very general result that holds for general commutative rings. So we began with the definition of commutative rings and examples. So commutative rings and examples. So these are the four things we did last time. So let's proceed from there. So the next topic I want to deal with is ideals. So ideals and rings. From now on, whenever I'm going to talk about rings, I will always mean commutative ring with identity. Commutative ring with 1. Even if I don't say that, when I say ring, this is what I mean. A commutative ring with 1. So an ideal in such a ring, so I subset of R, we know as an ideal, if it is closed under minus and closed under multiplication by elements of R. And if we also know that when you have an ideal of R, you can form the quotient ring. So we may form the quotient ring R mod I. And further, there is a ring homomorphism usually denoted by pi going from R to R mod I, which is surjective onto pi of any element A in R is A plus I, the coset. So R mod I consists of cosets of all elements of R with respect to I, and pi of A is A plus I. So every ideal will give you a quotient. So when we discussed examples of rings, since I hadn't done ideals at that point, I didn't mention this. So a large variety of examples of rings will come from the quotient construction. So we may form many rings by taking quotients of known rings. By ideals. So for example, if I take the polynomial ring in two variables, a, x, y, that's a ring, and I could take the quotient by some ideal I, where maybe I is the ideal generated by x squared plus y squared. So that's a quotient ring of kxy. This way, you can take any ideal in kxy and take the quotient. So you'll get plenty of examples of rings, and these rings all have, depending on what you're quotienting by, they will have very different kinds of properties. So we are going to see some of those a little later, but for now I want to concentrate on the Chinese remainder. Okay, So I also want to note that we know all the ideals in the ring Z. So in Z, we know all the ideals. What do we mean by we know all the ideals? So what we mean by we know all the ideals is I can give you a list, right? So they are the ideal 0, which has only 0 in it, and the ideal generated by n, which is all the multiples of n for any positive integer n. So this is a complete list of every ideal in Z. Every ideal in Z is either the 0 ideal, which has only the 0 element in it, or it consists of all multiples of some positive integer n. This is an important result. This is an important result because it tells you the complete ideal structure of that ring. Usually, you will not be able to say in a ring, if I ask you what are all the ideals in the ring, usually you will not be able to answer this question. But because the ring Z is so simple, we have a nice answer to this. Also remember that in any field, the only ideals are 0 and the whole field. Right? Okay. So I don't think do I need to go through the proof of why these are the only ideals in Z? It's clear that all of these are ideals, but that these are the only ideals. Do I need to go through this proof? Somebody say yes or no.
No.
Sorry?
No, sir. No, I don't want the proof.
Don't need the proof. Very good. Yeah. Okay. This is a very simple proof, right? It just depends on the Euclidean algorithm and we can prove this. So in Z, all the ideals are of the form nz and 0. In any field, the only ideals are 0 and 0. Okay. So what about ideals in some of the other rings? So in Kxy, for example, there are plenty of ideals. I'll just give you some examples, right? So some of these, one class of these are called monomial ideals. One class of ideals in Kxy. Monomial ideals. So what are the monomial ideals? Monomial ideals are ideals generated by a set of monomials. So just take any collection of monomials in X and Y and take the ideal that they generate. So it's important to understand what is the meaning of the term generated ideal. I'm coming to that, but first let me give you examples. So examples of monomial ideals are, for example, I could take the monomials x squared and xy. So this is two monomials. It's an ideal generated by these two monomials. For example, you could take the ideal generated by x cubed, x squared y, xy square, and y cubed. This is another ideal. This is generated by four monomials. Like this, you can take any collection of monomials in x and y and take the ideal that they generate. So let me come back to what does it mean to say generated ideal. So what's the meaning of the term generated ideal? So this I'll do in any ring. If R is any ring, and A1 up to AK are some elements in R, some K elements. Then the ideal I generated by A1 up to AK. It's written like this, right? This means the ideal I generated by A1 up to AK has two descriptions. One is an internal description and one is an external description. So external description is the following. External is the smallest ideal of R that contains all of A1 up to AK. This is one way of saying. That is, among all ideals of R which contain A1 up to AK, you take every ideal of R which contains A1 up to AK. How do you know there is some ideal of R which contains A1 up to AK? For example, R itself is an ideal of R which contains A1 up to AK. So just take the collection of ideals of R containing A1 up to AK and take the intersection of all of them. We will see shortly that intersection of ideals is still an ideal. So this forms an ideal and it's the smallest ideal which contains A1 up to AK. This is one way of saying the ideal generated by A1 up to AK. This is called the so-called external description. Then there is an internal description, which is often what we use usually. Internal. So take the collection of all R1A1 plus R2A2 up to RKAK, where the Ri's belong to R. That is, you take all linear combinations of A1 up to AK, but the linear combinations are taken with coefficients in the ring R. Take the collection of all such linear combinations, one can show that they form an ideal. So these form the ideal. Okay, so these are two descriptions of the ideal generated by a set of elements. So in particular, if we go back, monomial ideals are ideals generated by a set of monomials. But of course, there is no real restriction on taking just monomial ideals. KXY has many other ideals. Any ring has. You can just take any collection of elements in that ring and take the ideal generated by those. So that will give you plenty of examples of ideals. Okay. Okay, let's see what we do next. Okay, of the examples of rings I gave last time, right? So recall, we have the rings Z adjoined I and Z adjoined omega from last time. These are two examples of ring I gave. These are the examples, kinds of rings that arise in, say, algebraic number theory. So what about ideals here? So what are the ideals in this ring? What are the ideals in these? Now, it's a fact, which maybe I will try to prove next time if I need it, that both of these rings are examples of Euclidean domains. Both are Euclidean domains. Which means there is a version of the Euclidean algorithm which works for these rings. And hence, it's a result that they are both principal ideal domains. Hence, they are PIDs. So every ideal is generated by one element. So in these rings, every ideal is generated by one element. So examples of ideals. So in Zi, for example, the ideal generated by 3 plus 4i, that's an ideal. Or the ideal generated by 1 plus I, that's an ideal. Or the ideal generated by 2, that's an ideal. So every ideal is of this form. You just take one element in that thing and consider the ideal that it generates. So notice that even if you take two different elements, you might get the same ideal. So it's quite possible. For the ideal generated by A to be equal to the ideal generated by B, even if A is not equal to B. So let's just give an example. For example, the ideal generated by 1 plus I and the ideal generated by 1 minus I are the same ideal. I claim that the ideal generated by 1 plus I and the ideal generated by 1 minus I are the same. So how do we prove some statement like this? If you want to show that two ideals are the same, you have to show that every element on this side is an element on that side and conversely. So note that. So if I call this ideal I and if I call this ideal J, I want to prove that I and J are equal. So note that it is enough to show that 1 plus I belongs to J and 1 minus I belongs to I. If I show this much, then of course I and J will be equal, right? If the generating elements belong to the other side, then these ideals will have containment relations and so they will be equal. So
both are associates elements, therefore.
Exactly. Both are associate elements, both are related by a unit. That's the fact. So just take, I into 1 plus I. If I take I into 1 plus I, it is I minus 1. And so minus I into 1 plus I is 1 minus I. So that means this 1 minus I belongs to the ideal generated by 1 plus I. And similarly, you can show the other way around. So in general, in a ring, the ideal generated by A is equal to the ideal generated by B. Okay, let me say let me not say ring. Let me just say for now integral domain. It's probably true otherwise also. If and only if A is equal to UB for some unit. Unit means invertible element of that ring. So two things generate the same ideal if they are related by units. And 1 plus I and 1 minus I are related by this unit minus I on one side, right? And so they generate the same ideal. In general, if I just give you generators of ideals and ask you if some element belongs there or not, it's not easy to decide. You may not be able to say very easily unless the ring is very easy. Unless simple rings like PIDs or fields have no ideals almost. There it's okay, but otherwise you will not be able to say in general whether an element belongs to an ideal or does not belong to an ideal. It's not easy to do. Okay. So let's see if I have more examples of ideals. Yeah, so that's it. So that's the next thing I wanted. So ideals and quotients. So next, let's move on to what can we do with ideals, right? What can we do with ideals? Now, just like elements in a ring, you can add and you can multiply. You can also add and multiply ideals. So there are, in fact, 3 important operations that you can do to a pair of ideals. So there are 3 important operations. That can be done with ideals. So the first one is sum of ideals. So if I and J are ideals in R, then you define I plus J to be the smallest ideal containing both I and J. This is the external description, right? You can say, take the smallest ideal of R, which contains both I and J, and that ideal I want to call the sum of I and J. But there is an internal description. You can take, this is also the same as the set of all I plus J, where I belongs to I and J belongs to J. It's a collection of all elements of the ring of the form I plus J, where I is in I and J is in J. You can check that this is an ideal. It's closed under subtraction and closed under multiplication by elements of R. So this is an ideal, and this ideal is the sum of I and J. And one can also check that it is the smallest ideal which contains both I and J. You have to check that this contains I, that this contains J, and any ideal which contains both I and J contains this particular ideal. Right? So this is the sum of I and J. So even in Z itself, the sum operation is an interesting operation. So let's just see what happens in Z. For example, so let us, for example, take, consider Z. The ideals 6Z and 15Z. Right? All multiples of 6 form an ideal, all multiples of 15 form an ideal. So we have these two ideals. What is the sum? So what is 6Z plus 15Z?
GCD of 6 from.
Yes, exactly. So the sum of these two ideals means the smallest ideal, which should contain 6 also, which should contain 15 also. If it contains 6 and 15, of course it will contain 12. And since it contains 12 and 15, it will contain 3. So any ideal which contains 6 and 15 will contain 3. And one can show that 6Z plus 15Z is actually equal to 3Z. Certainly 3Z is contained in the sum. I claim that it's exactly equal to the sum. Right? So in general, MZ plus NZ is the GCD of Mn Z. This is how you add ideals in Z. Since every ideal of Z is one generated, we know that MZ plus NZ is generated by one element. And which one element is it? There are two possibilities. It could be either the GCD of Mn or the negative of the GCD of Mn. But if you just stick to positive numbers, it's just generated by MNZ. Right? So the sum of ideals in Z is this. So this is an operation that you can perform on ideals. So one thing I want to mention about this operation is, so for any ring R, if I is the ideal generated by A1 up to AK, and J is the ideal generated by B1 up to BL, then I plus J is simply the ideal generated by all of them, A1 up to AK and B1 up to BL. So usually you will specify an ideal in a ring by giving what its generators are. So you will say the ideal in the ring generated by such and such. So in terms of that, it's very easy to add ideals. You just put the set of generators together, whichever ideal you get, that is the sum of I and J. Sometimes it could happen that the sum of two ideals is the whole ring R. Remember that the whole ring R is also an ideal. So R itself is an ideal of R. And sometimes I plus J could be the whole of R. So for example, 2Z if I take plus 3Z, as I just said, it's generated by the GCD. The GCD of 2 and 3 is 1. So it's just 1Z. 1Z means Z. That means 2Z plus 3Z equals Z. Another way of saying this is the ideal generated by 2 and 3 in Z is Z itself. Another way of saying this is The ideal generated by 2 and 3 means what? It's all numbers of the form 2a plus 3b, such that a and b are in Z. So the collection of all numbers of the form 2a plus 3b, where a and b are in Z, is the whole of Z. Every element of Z can be represented as 2a plus 3b for some a and b in Z. Okay, so this is about the sum of ideals. So this is one operation that you can do on ideals. The other operation you can do on ideals is the operation of product.
So we call this a co-maximal, right?
Pardon? Yes.
So these ideals are co-maximal.
Yes. So ideals which sum to R are called co-maximal. So definition: if I plus j is R, we say that I and j are co-maximal ideals. And this definition
we
is
need
going
the
to
intersection is singleton zero.
Sorry?
We need the intersection should be 0, right?
No. Intersection need not be 0. It's only that the sum must be R. That's all. That is something to do with the direct sum. That's a different thing altogether. No, intersection need not be 0. It's just the sum of the two ideals R. That's all. For example, 2 and if you say 2z and 3z, 2z intersect 3z if you do, that means every number which is divisible by both 2 and 3. That's obviously 6z. That's not the 0 ideal, right? That's not 0. But 2 and 3, 2z and 3z are co-maximal ideals. Okay, the intersection need not be 0. Fine. Okay, so now let me get to the next operation on ideals, which is product. This operation one must be a little bit careful about. So if I and j are ideals of R, then we define Ij to be the ideal generated by all little I, little j, where I is in I and j is in j. The difference between the product and the sum is, for the sum of two ideals, we just said you take all the I plus j's, they form an ideal, and that is the ideal. But here, that's not the case. If I just take all the ij's, where I is in I and j is in j, that collection is usually not an ideal. Right? In rings such as Z, it will happen that it is an ideal, but that's only because the ring is easy. Usually, if you take the collection of all ij's, where I is in I and j is in j in a ring, it will not form an ideal. So let's just take an example. So let us take the ring, polynomial ring in 4 variables, x, y, u, v. Okay, this is a ring, right? K is a field. I'm taking a polynomial ring in 4 variables over this field. So in this, I want to consider the ideal I, which is generated by x and y. That means all polynomials which can be written as x times some polynomial plus y times some other polynomial. And I want to take the ideal j to be generated by u and v. Similarly, all polynomials which can be written as u times something plus v times something else. So now I want to see what is the ideal ij. So by definition, you have to take every element of I and every element of j, multiply all of them, and take the ideal generated by all of those hugely infinite sets. Okay, but in this case, if you know generators for I and generators for j, you can write down generators for ij. So let me just first say that. It is the ideal generated by xu, xv, yu, and yv. You take every generator of I, multiply with every generator of j, and take that collection, the ideal generated by all of those, that's what is ij. It can be shown from the definition, right? The way I have defined it is not this, but it can be shown from the definition that it's the ideal generated by this. Note, what I want you to note is, note that if xu plus yv belongs to this ideal, the element xu plus yv belongs to this ideal because xu belongs there, yv belongs there. So the sum of those two will certainly belong to ij. But it cannot be written as a product, but it is not of the form ij, where I is in I and j is in j. So this is one thing about the product. You always, when you're working with the product, you have to remember that it's not just the collection of all ij's. That is not the ideal ij. It's the collection of all ij's, the ideal generated by that set, which is different from the way sum is. Okay. So, and as I said, so let me make this small claim. If I is generated by A1 up to AK and J is generated by B1 up to BL, then the ideal IJ is generated by all of the products A1, B1 up to AKBL. So when I'm saying that this is a claim, right, it needs proof. So I want you to think about why this is correct, right? Just based on whatever definitions I have given. So I have defined what is ij, right? I have defined ij to be the ideal generated by all ij, where I is in I and j is in j. And here I have the ideal, this ideal and this ideal. I want you to show that the ideal ij is generated by all of these elements, right? So this is an exercise. First, understand what the meaning is. Then, if you understand what the meaning of the statement is, the proof is clear. This is an exercise. Okay. So now we have discussed two examples of operations on ideals. One is sum and one is product. And in the discussion, we also said one more operation, which is intersection. So that's the third operation, intersection of ideals. So if I and j are ideals of R, then I intersect j is also an ideal of R. It's very easy to show. What do you mean show? You have to show that it's closed under differences and closed under product by an arbitrary element of R, both of which are easy to see. So this is the third operation on ideals. So what happens? Again, let us try and see examples of this operation in Z. So in Z, for instance, in Z, what is the intersection of 6Z and 15Z? That means I want elements which are divisible by 6 also, right? And they should be divisible by 15 also. So they should be divisible by 6 and 15. Of course, they should be divisible by the LCM. 30. Yeah, exactly. 30. So they should be divisible by the LCM of 6 and 15, which is 30. So this is 30Z. Again, this is the general fact. In general, MZ intersect NZ is, I'm using square bracket to stand for the LCM, right? So this is the LCM of MN. Round bracket stands for GCD, square bracket stands for LCM. So MZ intersect NZ is generated by the LCM of MNN times Z. Again, intersection of ideals. is not very easy to calculate. Sum is very easy to calculate. If you know the generators of I and j, you just put the generators of I and j together, that will generate the sum. Product is also easy to calculate. If you know the generators of I and j, you just multiply every generator of I and every generator of j. Whatever you get will generate ij. But in contrast, the intersection is usually not easy to calculate. In case of z, which is not a very difficult ring, it's easy. Or in general, if you have a PID, it's not hard to calculate the intersection. But if the ring is not a PID, usually it is not going to be easy to calculate the intersection. For example, in KXY. So this is the first example of a ring which is little more complicated than a PID is, right? This is not a PID. Now, ideals here are not usually generated by one element. You could have ideals which require a large number of elements in this string. So in this string, if you take the ideal x squared y, the ideal generated by x squared and y, that's a monomial, right? And intersect it with the ideal generated by x and y square. If I were to ask you what the answer is, so what is the ideal, which is the intersection of these two, it needs a little bit of work to prove. It's not extremely difficult, but it needs work to prove. The ideal is actually, it's generated by x squared, xy, and y squared. Okay, so this is a slightly harder exercise than before. It's not that easy. If I were to ask you to prove this, you will need to do some work to do this. So, but it's a good exercise for you to try. Try to prove this. Careful. So you must show that this thing is contained in each of those ideals. That's easy to see. But what is harder to see is if something belongs to this ideal and to this ideal, then you want to see that it belongs to the ideal x squared, xy, and y squared. That means anything which is expressible as a combination of the polynomials x squared and y, and also expressible as a combination of x and y square, is necessarily expressible as a combination of x squared, xy, and y squared. All of them with coefficients coming from the ring KXY. Right? So try and prove this.
So the intersection always contains the product.
Yes, I'm coming to it. Yeah. So now I want to see what are the things about the relations between this intersection, sum, product, what kind of properties that they have. Okay. So the first thing is, so properties of ideal operations. So one easy property is the following, which is that the product distributes over sum. In other words, what does this mean? That means if I take I times j plus k, this is ij plus ik. This is one property, and it's easy to see. I mean, it's easy to see in many ways, but let me just give a proof, assuming that these ideals have some finite sets of generators. So suppose I is generated by a1 up to ak, j is generated by b1 up to bl, and k is generated by some c1 up to cm. Right? So we have three ideals. I is generated by some things, j is generated by some things, and k is generated by some other things. So what is j plus k? I already told you that j plus k is generated by the generators for j and k put together. So it's generated by b1 up to bl and c1 up to cm. That is what is j plus k. Now what about I times j plus k? Products, we know how they generate. If you have generators for I and generators of something else, the generators for the product ideal are taken. You take the products of every generator of I with every generator of the other one. So in this case, every generator of I and every generator of j plus k you have to multiply. So all these a's have to be multiplied with all of these. So what will you have? You will have a1 b1 up to a1 cm. Then you'll have a2 b1 up to a2 cm. So on and so forth up to ak b1 up to ak cm. So this is what is I times j plus k. On the other hand, what is ij? Ij is generated by just the products of the a's and the b's. So this is just all a1 b1 up to ak bl. And ik is all the a1 c1 up to ak cm. And what is the sum of these two? Ij plus ik is generated by all of these put together. That is a1 b1 up to ak bl and a1 c1 up to ak cm. And you can see that this and this are the same. Just only the ordering is different, right? Only the ordering of the terms is different. In both, you will have every term of every ai multiplied with every b and every c. So I times j plus k is ij plus ik. But this can be proved even independently, even from definition of what ij means, what ik means. You can also prove this independently. So another exercise. Prove I into j plus k equals ij plus ik without using generators. I used generators to do it, but it can be done without using generators also, and try and think of how it would be done, right? Okay, so this is one property that the intersection of the product has with respect to the sum. In contrast, the intersection does not distribute over the product, right? So this is, we have to note this. Note intersection does not distribute over some sort in general. In general means in certain rings it might happen, in Z it might happen, or in some small in a PID it might happen, right? But usually it will not happen that the intersection distributes over some. So let's first give an example to show that this is false. So what does it mean? I intersect j plus k is not equal to I intersect j plus I intersect k in general. I'm not saying it's not always equal. It could happen in some examples, but this is not a theorem, right? You cannot prove this because there are cases of ideals for which this is false. So let's first look at an example where this is false. Okay. So the example is not, again, when we want to look at examples of bad behavior, so you should look at rings which are complicated rings, right? Simple rings, everything will behave nicely, and you might think that things are true. But if you want to look at things, if you want to find counter examples to things, you must make the ring bad. Bad ring is kxy for us. Okay, it's not too bad a ring, but for our purposes, it's a bad ring. So take R equals kxy. Ring is kxy. K is a field. X and y are variables. Polynomial ring in two variables. In this, I want to give you examples of ideals I, j, and k for which this is false. So let us take j to be the ideal generated by x. It's a principal ideal. That means all multiples of x, x times every polynomial. And k to be the ideal generated by y. Okay. Then you know that j plus k is therefore the ideal generated by x and y. That's how you do plus of ideals. You just take generators of each, put them together.
So please change the notation, sir. I already used the k.
Yeah. Okay, let's make this small k, right? Let small k be the field, big k is the ideal. Okay. So now I want to take I to be the ideal generated by x minus y. That means all multiples of the polynomial x minus y. That means x minus y times every polynomial in R. Now I claim that I intersect j plus k is different from I intersect j plus I intersect k. So let's do this calculation. First, what is I intersect j plus k? I is the ideal generated by x minus y. And j plus k is the ideal generated by x and y. But here you notice one thing. Notice that the element x minus y already belongs to this ideal, right? The ideal generated by x minus y certainly contains the element x minus y. So that means x minus y is there. That means the whole ideal generated by this is a subset of this. That means the intersection is just x minus y. So I intersect j plus k is just I itself in this example. It's more interesting to see what is I intersect j and I intersect k. Now that's a more interesting thing. So let us try and see what is I intersect j. I intersect j is x minus y intersect x. This means this is all polynomials which are divisible by x minus y and also by x. If you have a polynomial which is divisible by x minus y and x, one can show this. One can show that because this thing is a unique factorization domain, one can show that in fact, so this is not completely trivial. So I'll just say can be shown. That this is the ideal generated by x squared minus xy. So the ideal I intersect j is the ideal generated by x squared minus xy. On the other hand, the ideal I intersect k similarly is x minus y intersect y. Again, this can be shown that this is xy minus y squared. And so the sum of these two, so if I take I intersect j plus I intersect k equals the ideal generated by x squared minus xy and xy minus y squared. This is the ideal generated by the ideal I intersect j plus I intersect k. I claim that this ideal is not equal to the ideal generated by x minus y. It's smaller, in fact. This ideal is contained in the ideal generated by x minus y, but is definitely not equal. So why is it not equal? Okay, why is it not equal? Not equal because any polynomial in the ideal generated by x squared minus xy and xy minus x squared must be of degree at least 2. Already these are of degree 2. You're multiplying two things and adding. Okay, it needs a little bit of proof, and even allowing for cancellation, one can show that any polynomial in this ideal is of degree at least 2, but x minus y is of degree 1. So it cannot belong to this ideal. Okay, this needs proof. Okay, so but anyway, it can be done. So this is an example where this distributive law doesn't hold for intersection over sum. But as I said, it's contained. So, and that is true in general. In general, I intersect j plus k contains I intersect j plus I intersect k. That is easy to see. If something belongs to I and to j, of course that thing belongs to I and to, sorry, this is plus, not intersect. If something belongs to I and to j, of course it belongs to I and to j plus k. Similarly, if something belongs to I and to k, certainly it belongs to I intersect j plus k. And therefore, the sum of these two is contained in I intersect j plus k. This much is always true. But the other inclusion is not always true. But this is not always true. There is one case where the other inclusion holds, and that's called the modular law. And that states the following: I intersect j plus k equals I intersect j plus I intersect k if I contains j or I contains k. If I contains one of them, then it's correct. The intersection will commute over, will distribute over the sum. So let's prove this. So proof. Already we know that I intersect j plus k contains I intersect j plus I intersect k. Now we want to prove the other way. So we want to show the other way content. So that means I want to take an element of I intersect j plus k and show it belongs to the other side. So it belongs to the I intersect j plus I intersect. This is easy to do. Okay, so how is that? So take an element of I intersect j plus k. So suppose x belongs to I intersect j plus k. What does it mean that it belongs to I intersect j plus k? That means it should belong to I. So x belongs to I first. And further, it belongs to j plus k. So x can be written as j plus little k for j in j and k in k. So x belongs to I and x is equal to j plus k, where little j is in j and little k is in k. This much we know. So now let us see. So note that so x equal to j plus k. This belongs to I. This belongs to j. This belongs to k. But we have also said assume that I contains j or I contains k. So assume I contains j. Same proof with the other thing holds. So this implies that j, little j which is in j, is also in I. So that means this is also in I and this is also in I. That means k is in I. Hence k, which is x minus j, belongs to I also. That is, this element little k belongs to k also and belongs to I also. The element little j belongs to j, which is j intersect I, because j is contained in I. And so x, which is j plus k, belongs to is contained in I intersect j plus I intersect k. And that's what we wanted to show. Right? So the intersection distributes over the sum if I contains j or if I contains k. That is the so-called modular. So this is one thing to notice. Another thing to notice is the following. Also note that the following containments hold. And these containments are the following. That is I plus j times I intersect j is contained in ij, is contained in I intersect J. For any two ideals I and J. This is a very general thing. In any ring. So how do we prove this one? So why do these containments hold? So for example, if I take something in I plus J and multiply, so what am I saying here? I'm saying if I take an element of I plus J and an element of I intersect J and multiply the two, the result belongs to Ij. Okay. So let's try to prove this. So take any element I plus J in I plus J and any element in I intersect J, I'll call that K. In I intersect J. So we want to show that little I plus J times K belongs to Ij. But what is Ij? Ij is generated by all the products of elements of I and elements of J. That's how we define Ij. I plus J into K equals Ik plus Jk. Now, these two terms, I'll show that both belong to Ij. Ik belongs to Ij because this I belongs to I and this K belongs to I intersect J, which is contained in J, of course. Right? So Ik belongs to Ij. Similarly, Jk belongs to Ij because this belongs to J and this belongs to I intersect J, which is contained in I. So both elements belong to Ij, which implies that I plus Jk belongs to Ij, the ideal Ij. So that proves that first containment. So that proves that we have finished this one. We have proved that I plus J times I intersect J is contained in Ij. And secondly, Ij is contained in I intersect J. This is even easier to prove. Why is Ij contained in I intersect J? What does Ij mean? Ij means the ideal generated by all the Ij's, where I is in I and J is in J. That's the definition. But each of these generators belongs both to I and to J. So each of these is in both I and J. Because it's the product of an element of I with something, it's in I, capital I. Because it's the product of an element of J with something, it belongs to capital J. So each of these is in both I and J. So Ij is contained in I intersect J. So we have this law, which is I plus J times I intersect J is contained in Ij, is contained in I intersect J. So this leads to one useful corollary. And this is relevant for us in the context of the Chinese remainder theorem. The corollary is that if I and J are co-maximal, and recall that means I plus J is R. Then I intersect J equals Ij. Okay, remember that I intersect J usually is an Ij is usually a smaller ideal than I intersect J, but sometimes they could be equal. And one condition under which they are equal is that if I and J are co-maximal. So let's again go back to this example. So we know that 6z intersect 15z. So what was the answer to this? Something divisible by both 6 and 15 is divisible by 30 is 30z. And what is 6z times 15z? This 90z. Notice that these two are definitely not equal, right? I intersect J and ij are not equal here. But that's because 6z and 15z are not co-maximal. 6z plus 15z, we already said is 3z. So 6z and 15z are not co-maximal. If they were co-maximal, then it would have happened. So for co-maximal ideals, I intersect j is equal to ij. Okay, so that much about operations on ideals. Okay. So next thing I need in order to do the Chinese remainder theorem is operation on rings. Okay. So constructing new rings from old. So in general, if you have just give me a second. Yeah. So you want to get examples of rings, right? We already have one collection of examples of rings, and I told you how to get some more. One way of getting new rings from old is by the quotient construction. You could take a ring and an ideal in that ring and take the quotient ring, that gives you a new ring. So this gives you a way of getting new rings from old. But there are other constructions. For example, you know from group theory that if you have G and H are groups, then you can form a new group called G cross H, right? That's a construction which gives you a bigger group G cross H from two small groups G and H. Similarly, there is a product construction for rings. So if R1, R2, up to Rk are rings, then we may form the product ring. R, which is written as R1 cross R2 cross Rk. So what is this ring? So as I said, it is just the Cartesian product. Just the product of sets. Just the Cartesian product R1 cross R cross Rk, which is of course the set of all little r1, little r2 up to little rk, where little r1 is in r1, little r2 is in r2, so on up to little rk is in rk. That's a set. And how do you make it into a ring? So make it into a ring by component-wise addition and multiplication. Make it into a ring by component-wise plus and dot. That means what? That means if I take R1 Rk plus S1 up to Sk, the sum I'm going to define as R1 plus S1 up to Rk plus Sk. And the product of R1 Rk with S1 Sk is just equal to R1 S1 up to Rk Sk. Okay, wait, let me see. Somebody has raised their hand. 1 second.
Professor, you told me that constructing a ring in this form of Cartesian product is a unique way of construction, I think so. As far as a quotient ring is concerned, we can construct many number of rings. But as far as this Cartesian product is concerned, I think it's only one ring we can construct. Can we construct?
No, that's not true. That's not true. See, on the Cartesian product, you could have other ring structures which may not be very natural, but this is a very natural ring structure that you can put on the Cartesian product. The most natural one is this. Of course, the Cartesian product is just a set, right? Or you can think of it even as an abelian group. There will be other ring structures possibly you can do, but the natural one is this. Fine, this is the natural. Okay, so let's get back. So you make it into a ring by component-wise plus and dot. And notice that one thing you have to notice about this ring is all our rings, we want them to have an identity element. That is very, very important for us. Whenever you are studying commutative rings, at least when you are studying commutative algebra, every ring must have an identity element. So this ring had better have an identity element. Note that this R has an identity, which is what? Which is just the tuple 1, 1, 1, 1, where each of these ones is the identity of the corresponding R. Each of these ones is the multiplicative identity of the corresponding R. Ri. That means the first one is the identity of R1. The second one is the identity of R2. The last one is the identity of Rk. And one can check that this element, this tuple, is actually an identity for this ring. So this becomes a commutative ring with identity. You have to check various things. You have to check that addition is, usual things, associative, distributive, all these things. Everything will follow from the fact that originally the Ri's are rings. So this will also become a ring. So this is the product construction for rings. Okay, I think now we have enough to state the Chinese remainder theorem. This is for general rings. I am not assuming anything nice about the ring. I'm not assuming it's a principal ideal domain. I'm not assuming it is Z. I'm not assuming it's a polynomial ring. It is for any ring at all. So Chinese remainder theorem for a general ring. Of course, commutative ring, right? I'm only working with commutative ring. So let me see what's the best way to state this. 1 second. So it states the following. So let R be a ring. And I1, I2 up to Ik be ideals of R. Okay. Then there is a natural ring homomorphism. There's a natural ring homomorphism. Phi going from R to the product of all of these quotients, R mod I1 cross R mod I2 cross R mod Ik. And what is this natural ring homomorphism? It's defined by, if I take an element X in R, where does it go? I have to give you a tuple. It should be a K tuple. The first element of that K tuple should be in R mod I1. Second element of the K tuple should be in R mod I2, and so on and so forth. So I just take X bar, X bar, X bar. All the components are X bar. But you must notice that each X bar means a different thing. This X bar, the first X bar means X plus I1. The second X bar means X plus I2, the coset. The last X bar is X plus I2. So this is a map, and one can check, one should check that this is actually a homomorphism. It's easy to check. So check. This is the ring homomorphism. Okay. And the Chinese remainder theorem can be stated in some 3 parts. Actually, only one part is real Chinese remainder theorem. The other 2 parts are somewhat simple. So it says that the first part, which is very easy, says, so the kernel of phi is the intersection of all these ideals. That's the first and easy part. Second part says, if I sub I and I sub j are co-maximum, for every pair I and j not equal, then the intersection of all of these things is also equal to the product of all of these. Remember that intersection and product usually will not be the same, right? And we said for two ideals, the intersection and the product are the same when they are co-maximum. We are making the same statement for more than two. Suppose I have 10 ideals, and suppose any two of them are co-maximal, then I'm saying that the intersection of all the 10 and the product of all the 10 is the same. So that's the second statement. And the third statement is the actual Chinese remainder theorem, which says that phi is surjective. That's on to if and only if I sub I and I sub j are co-maximal whenever I is different from j. So finally, putting all this, so I will of course have to prove this the next time, but let me just mention one thing. So what does this say? So hence, when the ideals I sub I are pairwise co-maximal, the ring R mod I1 intersect IK is isomorphic to the ring R mod I1 cross R mod I2 cross R mod IK. That's what this Chinese remainder theorem finally says. Now, the way I have stated it here, it doesn't look like it has anything to do with either Lagrange interpolation or the other Chinese remainder theorem I said earlier. At least for the other Chinese remainder theorem, there is some resemblance, but it doesn't look like it has anything directly to do with Lagrange interpolation. We will see how this Chinese remainder theorem implies the original Chinese remainder theorem I did, as well as Lagrange interpolation, as well as something little more complicated than Lagrange interpolation called Hermite interpolation. So we will see this next time. So for now, I will stop here. And I'll just mention one thing. So I have asked Professor Gurusamy to share with you the notes, Atiyah McDonald's chapter 1 notes. I would like to do many of the things in chapter 1 at least. So in this course of lectures, I'd like to cover many of the things in chapter 1. The Chinese remainder theorem is one of the things, but there are others. So there are things about the nil radical, about the Jacobson radical, prime and maximal ideals in rings. And it has a wonderful set of exercises. So the book by Atiyah McDonald on commutative algebra is a very small book, right? It's very, maybe 120, 130 pages, I think. It's a small book, but it's really, if you do that book carefully, and what does do the book carefully mean? It means you read everything, right? Work out all the exercises. You will learn a substantial amount of commutative algebra if you do that. It's a short book, but it's very crisp and it's a very beautifully written book. So I'll be doing parts of chapter 1. And if we have time, maybe some parts of chapter 2 also from that. So we will stop here for today. Thank you.
Thank you, sir.
I'm not sure how to stop. Okay.
Okay.
Yes.
Thank you, sir.
Are there questions? Yes.
No.
Have somebody asked questions which I have not seen it's possible. The thing is, I'm seeing the screen on which I'm writing, and the other screen, which is the chat screen, is not visible to me all the time unless I click. So I won't know sometimes if you have asked questions.
Sir, in this, you are taking the ideals are finitely generated.
Yes.
That is necessary to.
No, it is not necessary. No, it's not necessary. The same proof works even if the ideal has an infinite number of generators. That's what I've asked you to do as an exercise. I've asked you to do independent of generators. Don't give a proof based on generators. The proof can be done without reference to any generators at all. It doesn't need finitely generated. No.
Okay.
Okay, so if there are no further questions.
So, and then please discuss about some finding the maximal ideals of polynomial in two variables.
Sorry, what?
Maximal ideals in polynomial in two variables. So how to,
Yes, I'm going to do that. I will do that.
Yeah.
We are going to discuss maximal ideals in polynomial rings next time. I'm going to do that.
Okay.
Okay, yes. So fine. Yeah, thank you all.
Thank you, sir.
Thank you, sir.
Sir.
Thank you, participants. We will meet once again in the next session. Probably tomorrow around 5:15 p.m. Thank you.